Hey kids, here we are again, ready to have another lesson. Notice your book homework tonight is in the book, and some of the directions say plot this conic section using the plot conic program on your computer, blah blah blah. Ignore. Okay, you're not going to have a calculator or a computer to graph these things. You will have a calculator if your numbers are too high. But just for calculation, not for graphing. You might want to pause the video while you work on this warm-up. Remember, I will be collecting the homework on Monday. We're going to stick with ellipses right now, and I hope you recognize that even though I say graph and label, and I give a very generic quadratic relation, that you are looking at the coefficient of x squared, the coefficient of y squared, and saying to yourself, self, A is 4, C is 36, A does not equal C, neither one of them are 0, but they both have the same sign. Therefore, this quadratic relation, without graphing, I know this is an ellipse. And since they are asking me to graph, I need graphing or standard form. Which means I need algebra, right? So I'm going to group my x's. And group my y's. And then I'm going to do what? Factor. Right? You're going to factor out the coefficient of the x squared and the coefficient of the y squared, and you should expect integers when you do this, right? We are just starting. You will always have these nice numbers. You're going to complete the square. You're going to divide 10 by 2, get 5, square it. You're going to divide 8 by 2, get -4, and square it. But then you're going to multiply 25 times 4 and add it to the right side. You're going to multiply 16 times 36. And also add it to the right side. And when you do that, using my calculator, this side is 144, another nice number. This side is 4 times x, and then positive 10 divided by 2. -8 divided by 2. And lastly, I need to do what on the right side? If I have an ellipse, what has to be on the right side? I need a 1. So I have to divide everybody by 144 in order to get this 1. 36 goes into 144. Guess how many times? So 4 goes into 104. Guess how many times? So aren't all these numbers nice, right? .36 is a perfect square. If you find yourself on a quiz or a test this unit and you don't end up with these nice integers, you've done something wrong. Alright, can you tell me the center? Right? Questions? The center is not 5, but our x is 6 because it's under the x stuff, and our y is 2 because it's under the y stuff. Which one of these numbers is bigger? 6 is bigger, right? Therefore, you know that this ellipse is longer in the x direction, so 6 must be A and 2 must be B. And now you can answer these questions, right? What is the length of the major axis? 2 times A, which is 12, and the minor axis is 2 times B, which is 4. Now I didn't label it. I haven't graphed and labeled it yet, right? So to graph and label it, and this is a straight equation, so I don't have to worry about dashed lines or, dashed curves or shading inside or outside. But I'm going to go to -5, 4, I'm going to radiate 6 units this way, 6 units this way in the x direction. -5 plus 6 is 1. -5 minus 6 is -11. And then I'm going to radiate only 2 up and 2 down. So I'm going to get -5, 4 plus 2 is 6, and 4 minus 2 is 2. And I get an ellipse that is longer in the x direction, as I expected. The ellipse is sad, as I also expected. And I have the center, the vertices, and the co-vertices labeled. Right? At the ends of the major axis are my vertices. So if anybody asked you to list your vertices would be -11, 4, and 1, 4. And your co-vertices at the end of the minor axes would be -5, 2, and -5, 6. Right? To find the co-vertices, I added and subtracted 2 to the y-coordinate, and I added and subtracted 6 from the x-coordinate for the vertices. Now you're going to need this graph, right? I'm going to refer back to this warm-up graph for our new objective. Now our new objective is not a new conic. There's something about ellipses I haven't told you yet. So keep this graph in your warm-up book open or handy, but get your notes and write down the geometric difference, not the algebraic difference, definition, not the algebraic. The graphing form or the general form is the algebraic definition of a circle and ellipse, but I want to give you the geometric one. The circle is the set of all points. The set of all points in a plane, and for us that's the Cartesian plane. Doesn't have to be, but it is for us. It can be any plane really, but for us we've been on the xy plane. That is equidistant from a fixed point. This means that somebody has to pick this point. Pick it and stick with it. It doesn't move. Somebody picks a point, and we call that point the center. Then somebody picks a distance. Pick a distance and keep that distance constant. So pick some distance, so this blue dot is a given distance from the center. And what I have to do is, in order to generate a circle, I have to keep this distance constant no matter where I go in the plane, right? Whee! That's a circle. That circle is created by fixing one point, picking one distance, and keeping that distance constant. An ellipse, however, is the set of all points in a plane, and for us that's going to be the XY plane, such that the sum of distances from two fixed points does not change, is constant. These two fixed points are not the center. The center is one point. So for an ellipse, I have to pick 2 points and stick with them. Those 2 points aren't going to change. But then I need to go a distance from this first point. I'm going to call it F1. And a distance from this second point called F2. And I'm going to add those distances together, and then I'm going to find all the points in the plane that have those same distances. So here's a point. There's the distances to each one of those points. So this is distance, let's pretend that's 1. Let's pretend that's a 1. Well, since it's right? And let's pretend this distance is 5. What is 5 plus 1? The sum of the distances is 6. Now I need to find another point such that the distance isn't 5 and 1, but the sum is 6. For instance, I need 4 and 2. I need a point that is 4 units away from F1 and 2 units away from F2. If you keep doing that, if you find all the points on a plane that satisfy that condition of the sum of the distances being the same, you will get not a circle, but an ellipse. These 2 points are called focal points. Focal point 1, focal point 2. There is still a center halfway between, and the set of all points whose sum of their distances is constant from the 2 focal points form an ellipse. If your focal points are horizontal, your ellipse will be long in the x direction. But if your focal points are vertical, if this is focal point 1 and this is focal point 2, my center's halfway in between there, the set of all points whose sum of distances is constant from those 2 focal points is a vertical ellipse. Focal points always lie on the major axis. Focal points are these 2 fixed points that someone chose. They are always on the major axis, and they are always inside the ellipse. Crazy, right? There is still a minor axis on both of these ellipses, right? There's still the minor axis here, the minor axis here, but the focal points are always on the major axis. Now, if I were with you, we would do this experiment together and I would prove this to you, but since I am not with you, I'm just going to have to draw it. I'm going to do a horizontally oriented ellipse. So here's focal point 1, here's focal point 2, here's the center. The set of our points whose sum of their distance is equidistant from those two focal points is this ellipse. Now you know that to radiate from the center up to one of the co-vertices we call B, right? That's the semi-minor axis. To radiate from the center not all the way to the vertex, but just to the focal point is called C. So A is the semi-major axis, B is the semi-minor axis, and C is a focal axis, semifocal axis, right? Hey, that is a right angle. Now, between A, B, and C, who's bigger? If B is the semi-minor axis, right, and C is the semifocal axis, I'm not sure. Now, by my drawing, C is bigger, but it doesn't have to be. But can you agree with me that no matter what, between A and B and C can duke it out, but A will always be the longest of all three of these, right? Because A goes from the center through the focal point, because the focal point is always on the major axis, and goes past it out to the the vertex, right? Now again, if I was with you, I could prove this to you, but now you're just going to have to take my word for it. That the semi-minor axis, which is B, forms a right axis with the semifocal axis, which is C. And A, which goes past the focal point out here, is longer than both B and C, and shockingly, exactly fits here. What? Well, you know why this is useful? Because Pythagoras, yes, hello, come in. I'm so glad you're here. If I know two of these sides, I can find the third, can't I? Well, with an ellipse, I generally know what? I know B, and I don't know C. What do I know? A. Why do I know them? Because in an ellipse that is horizontally oriented, A is the semi-major axis and is under the X stuff in the graphing form of the equation. B is under the Y stuff. So can't I use Pythagoras to find the focal length if asked? the focal length of an ellipse uses Pythagoras. And what does Pythagoras say? The square of the hypotenuse in our triangle, A is the big boy on the block. A is the hypotenuse. The square of the hypotenuse is equal to the sum of the squares of what? The sides of the right triangle. So of course, if I actually want the focal length, if I want the focal length, I need to solve this for C. And remember, a focal length is to the right and to the left. Right? C squared is equal to what? The long hypotenuse squared minus the shorter squared. This is how you find the focal length of an ellipse. So here's a little video that shows the sum of those distances from the two focal points being constant, and that constant distance is 10. Right? An ellipse is a set of all points such that for each point the sum of its distance is constant. Eccentricity is a characteristic of ellipses that we'll study another day, but I just wanted to show you this little graphic. Eccentricity measures how flat or how round an ellipse is, and guess what happens if the two focal points meet? You have a perfectly round ellipse, which we call a what? Circle. But notice here that as the focal length gets longer and longer and longer, they call the focal length C in this, right, which we do. Look what happens to the ellipse. Oh! If the ratio of the focal length to the semifocal to the semi-major is 1, you ain't got an ellipse. There's lots of cool videos about conic sections on YouTube. Please feel free to Google away. So remember, A is a distance. There's really a plus and a minus A, right? It's the distance from the center to the vertices along the major axes. B, which again is really a plus and minus, is the distance from the center to the vertex along what? The minor axes. And remember, we really call these co-vertices. C then, which really is plus or minus again, C is the distance from the center to what? A focal point. It is also always along which axis? Always along the major axis. So your new objective today, we're still with ellipses. The only thing that I'm adding today, when you graph and label an ellipse for all your homework problems, you're going to be doing the same thing you did last night, except you're going to be adding the focal points. So again, to recap, to find the focal points in an ellipse, the focal length comes from Pythagoras, where A is the hypotenuse. You want to solve for C, right? So subtract, so you get A squared minus B squared is equal to C squared. You take the square root of both sides. to find the focal coordinates, I take the x-coordinate of the center and add c to it, and subtract c from it. If I have an ellipse that is oriented horizontally, or I take the focal length and add and subtract it to the y-coordinate of the center if I have an ellipse that is oriented vertically. So let's go back to your warm-up and find and graph the focal points. So this was our warm-up, right? So open up your warm-up back again. We had graphed negative 5, 4, and we had the vertices and the co-vertices. Right? We had the vertices were Rx was 6, right? And that was A, since it was bigger than Ry, which was 2. So we had negative 5 plus 6 and negative 5 minus 6. Then for the co-vertices, we had negative 5, 4. We had negative 5, and then we had 4 plus 2. Down here for the other co-vertice, we had negative 5, 4 minus 2. How do we find now the focal length? We have A, we have B. We need our focal length equation where C is plus or minus the square root of 36 minus 4. You can leave this as plus or minus the square root of 32. You just need to know that in most, like SAT 2s, conic sections show up on SAT 2 tests. It's not going to look like that. There's a perfect square of 16 inside 32, a perfect square factor. So the square root of 16 is 4. And the factor that's left under the radical is 2. Again, I am absolutely fine if you leave your focal length as plus and minus the square root of 32. So what I want you to do on your graph, though, is I want these graphed. Forgot I wrote this out. C we just found to be plus or minus the square root of 32, which is the same as plus or minus 4 root 2. Always go to the major axis. Radiate from the center and mark these with a little star, right? So that you know they're different from the vertices. And label them. Now, you don't write that down. This is going left for root 2 and this is going right for root 2. That's not where I landed, right? I landed at negative 5, the x-coordinate of the center, plus 4 root 2, comma 4, and negative 5 minus 4 root 2, comma 4. Now, if c had been an integer, I would have just combined them, but you can just leave right? This is the x-coordinate, negative 5, you know. What is 4 root 2? Root 2 is like 1 point something, 4 times that, right? So negative, so this is negative 5 minus, right? Minus 4-ish. So negative 10-ish. It better be shorter than negative 11. Can you figure out why? Remember, what was the x-coordinate of this vertex? This was negative 11, comma 4, right? So the focal point can't be as far as negative 11. Also, the focal point can't be as far as 1, right? Because focal points are always inside the ellipse. So all of your ellipses now, so to get full credit for graphing, you need to have the center, vertices, co-vertices, and focal points. Those need to be graphed and labeled, and then of course your shape. So let's try this one. We don't have to do algebra with this. This is already in graphing form. Rx and Ry are different, and I have a 1 over here. Therefore, I'm dealing with an ellipse. I also have an inequality. Since I have an inequality with no equal sign underneath, I know I'm going to be sketching a dashed curve, and I'm going to be shading inside because it says less than 1. Let's get our information out. What is my center? Negative 1, 2, that's in quadrant 2, right? Rx is under the x stuff. Ry is under the y stuff. Who's bigger? 3 or 5? 5 is bigger. And if 5 is bigger, 5 is the big boy on the block. So 5 is A, and 3 is B. How do I find how far I radiate to the focal point? How far I radiate to the focal point is C, and for an ellipse, C is equal to plus or minus A squared minus B squared. In this case, C is an integer, isn't it? Remember, this is a distance, not a location. So there's my graph, my x and y axis labeled. My center is negative 1, 2. I'm longer in the y direction. My major axis is parallel to the y axis. My vertices are negative 1 and 2 plus 5, which is 7. Negative 1 and 2 minus 5, which is negative 3. Radiate to the right. Negative 1 plus 3. And, oh, this is a terrible location for this, right? The sun should be negative 1, 2, should be here. This is negative 1, 2 minus 3. Where are my focal points? Your focal length go from your center and radiate up and down. How far? 4 units up, 4 units down. So what are the coordinates, though, of my focal point? Keep the x-coordinate the same because you're going up and down, so that's negative 1. 2 plus 4 is 6. And that better be smaller than 7 to stay inside the ellipse. This focal point is -1, comma, to -4, which is -2, which better be before -3, so that my focal point stays inside the ellipse. Good? Alright, so again, your homework is to graph and label quadratic relations. They'll all be ellipses, but you're going to have to find and include the focal points. Find the focal length and then plot the focal points for each one of your ellipses.